Okay, I'm continuing to work on this Trav-Ler radio model 60A, but I noticed some interesting things. First off, the schematic diagram here has 25Z5, 4375, and an electrolytic capacitor here and an IF transformer here. Okay, so tube, capacitor, transformer. But if you notice on the chassis, we got tube, capacitor, tube, transformer. So on the diagram, this tube is over here and this capacitor is over here. Not a big deal, but it's a different chassis than what they're showing in the schematic diagram on the bottom of the radio. The tubes are the same. The lineup is different. They have 4375 and a 25Z5 here. The actual radio has 4375 is here, and the 25Z5 is in the back. So they have the 25Z5 over here where this capacitor is, and they have the 75 up here where the 25Z5 is. Doesn't matter, same tube line up. Just they're in a different arrangement. Not sure what this switch is, can't find it on the schematic, so apparently there is some difference in the schematic. So that's one thing I found. The rest of it's right. The 66, second IF, 6A7 converter, the tuning condenser and a coil, it's all the same, tuning condenser. Okay, then I found some other issues. They had two different bulbs in here. The one on the bottom was this 6.3 volt bulb, which is what I believe should be. That looks old and original, and it's a Mazda bulb. On the top, somebody had put in this 1487 bulb, and it's unmarked. It just says USA, but it's a 1487, and it's a 14 volt bulb. It don't belong in there. I don't think so anyway. I think this one is accurate, and this is a 6.3, so it should have been two 6.3 bulbs. The way they're connected here, there's a pair of green wires that come up, this one here and this one here, and they come off of a center tap resistor. One comes to the anode of this light bulb, and then there's this white wire which takes the power down to the anode of this white bulb. The other green one comes and connects to the ground of this bulb. And then there's a red wire that connects from the ground of this bulb and goes back. So the voltage is divided across these two tubes. Both anodes are connected to this green line. This green line connects to one tube and makes a circuit, and this red line connects to the top one and makes a circuit. Now, I don't imagine them using two bulbs. I don't think they did. I'm not thinking that this is 14 volts and this is 6 volts. That just doesn't make much sense. So the colors of the wires is just so you don't get confused as to which wire is which. It's not that they signify any other thing than that. By the way, getting these bulbs out was a real chore. Somebody had worked on this radio one time before. You can see they etched all this out in order to slide this down further. Looks like they cut it the wrong way, and then they realized they went the wrong way and they cut it the other way. And that was to set the tension on this string, probably change the dial cord when they put that light bulb in. And maybe when they were putting in the dial cord, they seen that one of the light bulbs was bad. And most likely it was like this one. And so they went ahead and they put in what they had, which was this. and they might have got confused because it's a 1487, which is a 14 volt tube, but the popular GE is an 1847, which is a bayonet tube. It's not a screw-in tube, but a GE 1847 is a 6.3 volt tube, which is what the radio would have needed. And so 1847, 1487, it'd be easy to make that mistake, right? Especially since it's a screw-in and the other one is a bayonet. So that was one of the things I found. There were a couple other issues I found. One is this goat shield doesn't really fit this tube, obviously, but that's okay. But this RF can cover is totally loose. You see they're riveted on, and this one's out of the rivet. It looks like it got bent here, and it popped it out of the rivet, so I got to fix that. Another issue that I got to fix is that I've noticed, besides this and the burnt tubes and making lights, make sure I get the right one. This cap is totally welded to the lid of the tube here, and it wouldn't come off. The tube glue, you can see, was all deteriorated, so the cap came off instead of the lid. That happens. I might be able to save this tube. The wire's fine. I can free this up, clean it up so it goes in and out easily, put some new glue on the top of the tube and solder that back to that cap. It just solders to the top center there. And that tube should be okay. If the tube's fine, I'll check the tube on my tube tester. If it's not fine, well, then it doesn't matter. We'll just have to replace it anyway. I haven't tested any of the tubes, but if it is good, I can resolder that. I can repair that tube and save a tube because, you know, they're rare. You don't want to just change them unless you have to. There won't be no reason not to. Okay, that takes me to that setup. Now, here's the next issue. Okay, so the next thing I found out, I did the filament string, and the 25Z5 is a 25 volt tube, obviously. The 43 is also a 25 volt tube. The 75 and these two are all 6.3 volt tubes. So when you add them up, it comes to 68.9 volts. So that's this much of the string is 68.9 volts. Obviously, it has to come up to 120. And on mine, it's a little higher. My mains runs around 126. Okay, but they have these two resistors here, which are 35 ohms each. So there's a 75 ohm power resistor on the chassis. That's that resistor right there. And all that resistor does is it has a sensor tap. These two go to one pilot light, and these two go to the other pilot light. So basically we have a resistor with a center tap, the resistor there. The first half is 35 ohms, actually it's 34 point something and 36 point something, so basically originally they were 35 ohms, give or take. So you got a 35 ohm resistor in the string, in the series line, that's paralleled with one of the pilot lights. Then you have another 35 ohm resistor, the second half of this resistor, that's paralleled with the other pilot light. And so these are 6.3 volt bulbs, so there needs to be 6.3 volts across these 35 ohm resistors. So I got 6.3, 6.3, that's another 12.6 added to this. And so 12 would bring this up to 80 volts, and the 0.6 and the 0.9 would bring it up another 1.5, so 81.5 volts total across one side of the line all the way to here. So the other 40 volts is dropped over this resistor that was wrapped on the line cord. That wire that's wrapped down the line cord dropped 40 volts, and of course that's cord would get hot, and they used to call these old line cord resisted cords, they called them curtain burners because they would get hot. And, you know, if they were not in a good ventilated area, they, like behind the couch or whatever, and they were up against a curtain, they would start a fire. They could start a fire. They would actually burn curtains, and so they were called curtain burners. They definitely don't want one on there. They don't make them anymore, haven't made them in years, and they're never going to make them again. So we've got to drop the voltage 40 volts, and that would give us 120. But I'm thinking we might even drop the voltage a little more. This radio doesn't need all that voltage to run. Mains, like I said, my mains is 126. So, you know, mains can be 125, 124, depending on where you are in relation to the transformer on the power grid. So what I'm thinking of doing, of course, there's three options to replace that. One is to use a power resistor, which would be this one here, is to give you an idea, is dropping 12 volts, 12.6 volts, this one, and I'm sure it gets hot, but we got to drop 40 volts. So you can get an idea of the size of the power resistor we would need, at least a 30 watt resistor, and it would get really hot, put a lot of heat underneath these tubes, and I don't want to do that, but that's one option. I've done that before on a casket radio for the same owner, and it got really, really hot. That was with replacing the rectifier with a diode. And that's another thing you can do, is replace the rectifier with a diode and put a limiting resistor in here. Normally replacing the rectifier with a diode is not a problem. On the radio that I was working on, that I did a diode replacement for a rectifier tube, it had a 300 ohm resistor that ran all the way across the back, high power resistor. You've probably seen the video. If not, it's in my videos. It was a cadet radio. You can search for cadet and you'll find it. And that resistor was bad, so I had to increase the resistance, the power dropping, because of the diodes. Plus I had to make up the power dropping of that gigantic power resistor that ran across the back of the chassis. And I ended up with a resistor that got really hot, had to dissipate a lot of heat. Well, there's another way to do it, which is to, in this case of this line cord, is to replace the line cord with a capacitor to drop the voltage. Now the issue there's only one issue, and I need to deal with that, but the issue there is using a capacitor does not get hot. I mean, none of these capacitors get hot. Capacitors don't get hot. However, capacitors don't pass DC. They only pass AC, which means that this radio, which was originally designed to run on 120 volts AC or DC, will no longer run on DC, because DC can't get through the capacitor that would be in the middle of the string here. It would stop the DC from going through if you'd hooked it up to 120 volts DC. But who has 120 volts DC? Nobody. Nobody uses DC. Back when this radio was made, a lot of the cities across the country in the United States were still on DC. I mean, the original electric grid was DC, and then they switched it over to AC. So most of the cities never seen DC, even some of the big ones like Atlanta and stuff, never seen DC, because by the time they got power grids, it was already AC. But some of the older towns like Boston and Philadelphia and Pennsylvania, Providence, Rhode Island, and, up in New England, where the technology began, they were already being wired DC. And so these radios originally were made to run on DC and AC, because AC was out at this point in time. But as the grid was replaced, all over that had the old DC to AC, then obviously they stopped making DC model radios that ran on 120 volts. They still make DC radios at this time, but they were farm radios and they were made for rural areas where you didn't have any power grid. And so they ran on a 90-volt battery. But this is not a battery radio, and this doesn't run on 90 volts. It runs on 120, 110 is what it was rated. You see, 110 at 60 hertz, or 25 hertz, or cycles. They called it cycles back then, on DC. So it ran on 25 cycles DC, or which is kind of confusing, or 100. Well, actually, they ran on DC or 120 volts, 60 cycles, 110 volts, 60 cycles, or 110 volts, 25 cycles. Europe, I believe, well, now they're on 50 cycles. But there were different parts of the country when AC was being rolled out that ran on 25 hertz and 25 cycles instead of 60 hertz or 60 cycles that we have today. So this radio was made to run in a lot of different scenarios, right? 110 volts, either 60 cycles or 25 cycles, or DC at 110 volts. Well, now we got the issue of we don't have 110 volts anymore. We haven't had 110 volts for a long time. All the mains now is one. Well, it went to 115. You remember when it was 115? If you remember back to the 80s, then it went to 117. You know, it's pretty much the standard, and it would go up or down depending on where you are. So most radios and electronics were rated at 120 because even at 115 or 117 standard, if you was closer to the transformer, you'd be up to around 120, 119, 120, 121. And if you were further away, you would be down at least at 115 or 117, depending on the standard in your area. But now the standard is 120. So if you're near the transformer, like I'm pretty close to the transformer, they're on poles. They'll be so far down the road, right? Well, I'm close to the transformer. My mains runs at 126. So even if I got this radio wired for 110 the way it was according to schematic, which I don't even know that I can do that because I don't know what some of the components drop. But even if I could, I would be running at 16 volts below what I'm putting in it, and that's too much voltage for these tubes in the pilot light. So, I don't want to gear it for 110 volts, the original. I want to gear it for at least 120 volts. And then if you get 126, it's distributed, that 6 volts is distributed across everything. The filaments will be fine. These tubes are all rated at 0.3 amps. So you got 30 amps, 300 milliamps of current going through each of the tubes. That's the max. You don't want to go beyond that. So I'm going to set it up so that it'll run on like 120 volts AC with a current that's around 300 milliamps, which is what the tubes are meant to draw. That's what they'll try to draw. And that's all they should draw. And so I want to make sure that they don't have more current going through them than 300 milliamps. And so what I'll do is, to figure out the capacitance, it's a complicated formula, but what I'll do is bring it up on the variac when I got a capacitor in here. And once I'm drawing no more than 300 milliamps but close to it, I'll look at the voltage on my variac and say I'm at 117 or 120, 114, 117, somewhere around there. I can then add a power resistor in the circuit to make up the difference in the other few volts to get to the high end of the mains of around 125 or 120 at least, if that makes sense, so that we never increase the current beyond 0.3 amps. Okay, so those are the issues I found with the radio, and I got to figure this out. I got to figure out what size capacitance I need for the remainder of this. So I got to add the resistance, the drops across those resistors, should be 6.3 volts on each, because they each go to a 6.3 volt filament. If I use a capacitor, I'll probably have to put Zener diodes across here to make sure that the voltage stays at around 6.3 volts, 6 volts or so that when it's distributed across the tubes and the pilot lights, I want to make sure that it never distributes more than 6.3 volts or 6 volts or so across these pilot lights, so they never have a risk of getting hot, short life, or burning out. You want to make sure that, especially with onrush current, because that's the other issue with using a capacitor. When you put a capacitor in circuit, it has to charge. So when you first plug it in, it's like a dead short until it charges. Now, it takes a few microseconds to a couple milliseconds. It's really fast. You'd never notice it. But for that split little fraction of a second, the current is really high. Now, the tubes can handle that. That's not a problem. They just can't handle it sustained. But the lights can't. They'll blow out immediately. They'll just, like a camera light, flash, gone. They'll go real bright and burn out. So I've got to put a Zener diode over them to make sure that the voltage never gets below 6.3 volts across them. I mean above 6.3 volts across them. The Zener diode can take the flash. It's designed for it. But the light bulbs can't. Okay, so those are the issues. There's another issue, and it has to do with the schematic. So if I pull the schematic back up, it's an issue I found in the schematic. Now again, the schematic is for this tube radio. However, the tube layout is different than what the tube layout in the cabinet is showing. This schematic, we looked at it, does not show the filament string at all. So it doesn't show the pilot lights. It doesn't say that the pilot lights are 6.3 volts. Doesn't say they're 14 volts. Doesn't say one is 6.3 and one is 14 volts. It don't even tell you what the pilot lights are. It doesn't show that string. It doesn't show the string for the tube filaments. Now the DC version of this, the radio version of this, I'm talking about farm radio now, not power company DC, but batteries. This is the battery version of the radio. You see, it has the filament strings, actually, from the cathode heated. So these here are the filament strings, and they're in parallel. They're not in series on this. They're all parallel to ground. So, but this is a series string unit that they have to add up, and it doesn't show it anywhere. So we don't have that, and that's what I'm reproducing. I'm actually making the series string filament line for these tubes so that they can light up and conduct electricity. But what I did find out with the schematic is they have the wound. You see how they show the winding on the cord as a resistor? They just show it as a twisted pair, which is basically the resistor. They show these two funky symbols, which I still don't know what they are, but I'm assuming that that's the indication of the filament string goes across the line cord, including that resistor that we just looked at and the pilot lights. None of that's in this circuit. That resistor ain't even in here that the pilot lights are connected to. It's not in the schematic. But what is in the schematic is this choke coil, which is rated at 400 ohms. Now this is an impossibility. There's no way that they're going to pay to put an expensive choke coil in here. They're very expensive to make, even back then. I mean, they were cheap compared to what it would cost to make one today. But for back then, they made coils all the time. You see coils all over the place, right? Well, they made this choke coil, according to the schematic, and they put it in here, and one side connects to the line, to one side of the line cord, and the other side connects to ground. And they're saying that it's a 400 ohms DC resistance coil with a choke coil with an iron core. Okay, here's the problem with this. Notice that this line goes into the coil and then goes to ground, right? So you would think, okay, well, it's got voltage across it. No, this coil is useless in this circuit. According to the way the circuit is drawn up, this is a waste of money. They just threw away a coil because they got this side here going to ground, and this side, if you follow the wire and continue, look where it goes, ground. So basically, this is going to ground, this is going to ground. It's just a dead short across the coil. It's useless. The coil's not being used at all. It's like not even connected. I mean, you know, it's connected, but it's connected to itself. It ain't doing nothing. See that? You got to watch when you're working on these old radios, because even engineers back then made mistakes, and they were a lot more intelligent than a lot of the engineers today. They were actually designing tubes and designing all of this stuff. It's amazing what they could pull off with the limited technology of the day. Just unbelievable feats. Yet, they're infallible, and things like this happen. Now, it could be just not an engineer era, but although I believe engineers made all the schematics, could have been someone who drew the schematic for an engineer, but you know, that's unlikely. This is something that they traditionally did back then. They designed the circuit and they designed it on paper. In fact, you look at the schematic, you see it's like drawn with, you know, a certain amount of expertise as far as mechanical drawing is concerned, but not that great. They used straight edges, and they had templates for coils and IF cans and stuff. But a lot of places, the numbers are blurry. They're just handwritten numbers, you see. They're not typed numbers, and so, you know, and then they were sent to the patent office like that. So this one was definitely patented like this, with a coil that goes from ground on one side, as you can see here, it's grounded, and ground on the other side. What I would assume, but I don't know, is that this coil on this side doesn't connect here. It's supposed to connect here, or here, or here, you know, across these capacitors. That would make much more sense. It's a choke coil. Actually, what would make a lot of sense is that it would be in the string. In other words, that this line would be broken here, and this would connect here, and this would be up here and in series with the string in the capacitor. In fact, that became a common practice in other radios and future radios as to reduce the hum, the 60 hertz hum. You would have a capacitor, and then you would have a coil, a pi filter is what it was. You'd have a capacitor, then you would have a choke coil in line on the positive side here. You'd have a choke coil in line, then you'd have another capacitor. So you had a capacitor cutting the hum, a choke coil cutting the hum, another capacitor cutting the hum, and this third capacitor wouldn't be here. You would use a choke coil, or some might have a third capacitor. Others would have this capacitor up here, not part of the main power line coming in, but at a lower voltage, on the other side of a voltage divider. So be careful when you're working on these schematics, because there are errors. Now, where does that choke coil go? I don't know. I don't know what the engineer had in mind for it. I don't know what it's supposed to be doing. I assume it's a hum-resisting coil, but going from ground to ground is useless. It's not doing nothing. You might as well just throw it back in the box on your shelf, because it's a waste of money. And I'm sure that's not what the engineer had in mind, but that's the way it's drawn out. So you got to watch these things. So we don't know the resistance of this coil. It's not mentioned. We don't have the filament string. It's not mentioned. We don't even have the pilot lights. They're not showing. We don't know the voltage of the pilot lights. They're not given. And we don't have the resistor that goes in the filament string that powers the pilot lights. Yet we have a resistor line cord that we know is bad, and that's why it was never replaced, even though it's in terrible shape. So that's where we're at. Thanks for watching the video. Next step is for me to get the right capacitor, and I'll probably show that process in the next video. Thanks for watching. Well, this is the Trav-Ler. I did have music coming out of this, by the way. What I did is I put a capacitor here to replace the line cord resistor, and I put my voltmeter across a filament of one of the 6.3 volt tubes, and I just brought my variac up with the light limiting bulb up to about 5 volts on the filament. It did have a screech. I plugged in my little rinky-dink antenna and the screech was there, but if I kept the voltage at a medium range on the heaters, it would play, and I put it on a local channel and it was playing a song. So I know I can get that to work. A couple issues that I'm definitely aware of is that this chassis is not the chassis that's on the tube layout on the bottom of the radio. It's not the chassis that is on the schematic for a 60A. The tube layout is different, and the capacitor layout is different. However, I'm going to do my best to get it to play, because I was able to get some sound out of it. So what I just did now is to make it easier to see, I unsoldered these two, this one and this one here, from the chassis, because I got to get in here and find out where these electrolytic lines go so I can figure out which one is which. This one connects on the second, this one here, I don't even know what side's ground. And oh, there's the foil side. Okay, they got it backwards. Check that out. That's the outside foil side, but they had the hot side connected to ground. So I don't know. I got to figure that out. Maybe the chassis is positive. But they got the foil side connected to the second lug of this 5 lug, second from the right. I got the radio upside down. So second from the right lug of the 5 lug terminal strip. This one is connecting to, and this one here rather, is connecting to the pin 2. There's the heater pin. It's connecting to pin 2 of, I believe that's the 43. Yeah, because this is the rectifier. Yeah, pin 43, the output tube. Pin 2 coming from the heater. Heater being pin 1 and then pin 2. So I got them out of there. Now I have to figure out these wires. There's 3 capacitors in here and a ground. Three capacitor positive leads and a ground. And I got to trace them and try to figure out, based on this schematic, that's not the right schematic, but it's probably so close to the same, which one is which. But here's the strange part on this. They've got a 16 going from here to here, and I don't see a dot, but it has to connect there because it doesn't go past it. It doesn't connect here because the wire is going over it. So they got a 16 there, and they got a 12 here. So, and there is clearly dots on the 12. So if the 12 comes across here and the 16 comes across here, then we've got a 28 microfarad capacitor, basically, because they add up. They're in parallel. So that'd be a 28 microfarad capacitor. That just doesn't seem right to me. Seems like this one should continue on up and probably connect up here. But while it does, they both connect there. Yeah, that would be the B plus line. Okay. So yeah, they got both of these. You know, they didn't have high capacitors back then in 1935. And if they needed it, I guess they could put 2 together like that and do it. It's just really weird. And then the 8 microfarad just goes across one of the cathodes, connects to one of the cathodes of the rectifier tube. So I can find that one just by tracing the wire that goes to the rectifier tube. The other 2, one of them will go to ground. There's 4 wires coming out of the can, obviously. One will be chassis ground somewhere, which will be for all 3. And then one will go to the output transformer and a cathode. one of the cathodes, and then the other two, according to the schematic, will go to the other cathode. They'll go in parallel directly to the other cathode of 25Z5. So if that's the case, we can track that. We can find that, and then we'll know. We don't really need to worry about whether or not they're 12 and 16. I'll probably throw a, see, that's what, 28. I'll probably throw a 33 in there, which would be fine, and I think I got some 8s, but if not, I'll use a 10 for the other one. And the voltage should be, it's not going to be that high. It is rectified mains, so, you know, I'm thinking 160 would be fine. 160 volts. I would imagine that's what those would be. So, one of these goes directly to ground, and it should be black. Now the colors are worn out, you know. There's this one here that's going to this big old clob on the first lug. That's either ground or that's B+. Actually, that's ground. Okay, so there's the ground because it's actually a lug that's connected to the chassis. Big old glob of solder in there. So I would imagine that's ground, but I'll make absolutely sure that that lug is connected to that chassis. There's so many wires in there. Yeah, I would say it is. Okay, so we got that one, and this lug over here is also connected to the chassis. So it looks like the N2 are soldered to the chassis, and that's what's holding the terminal strip in. And so that one would be ground. And then here are the other three, and they're all going this way. One of them is going to pin, what is that, pin 8? 1, 2, 3, 4, 5, 6, pin 6 of the 75. And pin 6 of the 75, but it's also got to be going to the rectifier. It looks like it's going to the switch. And it's going to the heater. That's strange. Okay, so that's going right across the line, the heater string. And that's this one here. This one is going to here, which is pin 1, 2, 3, 4 of the 43. And they need to be going to this rectifier somehow. We got to figure that out. And then that braid, that's in a bad place. And then the other one here should be going to the same place, but it's not. It's going right by them. It's going up here. Now that one definitely is going to the rectifier. See, so I don't know. This may not be the same model as that schematic. This one is going to this pin of the rectifier tube. And it's this one here. And this one is not. So I'm not seeing two in parallel, but I'm going to check them out. So I've got these disconnected. I could go ahead and solder in some new ones, but I think I'm just going to leave them there for now so that they're not in my way. And this one I can move it around and get by it, and I'll just check continuity to find that. So that's where we're at. These little cans are interesting. They don't seem to have, what do they do? Oh, good. 0.01, 600 volts. Good deal. And hopefully they're all the same. That one looks a little smaller, but they seem to be marked. These are just weird, these sprays here, especially with the outside foil not going to ground. Wait a second. No, see, they're not. This one is. See, outside foil was connected to ground, but this one is not. The outside foil is the other end. So maybe that's a negative voltage there. That might be from one of the cathode grids, and it might be negative 2 volts or something, in which case that would make sense. But got to figure it out. So I'll set up this camera in a little bit, after I go get some lunch, and we'll trace these wires and figure out where they go, and then try to figure out what values we need to use, because I'm sure they're dead and there's no way of knowing what values they should be, because they're not on the can and we don't have the right schematic. So that's where I'm at. Thanks for watching.